Swayam Prabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering, and today we shall discuss about the second law applied to processes of a power plant. So, if we try to recall, in the last class we have discussed about the mathematical form of the combined first and second law, and if we apply this combine first and second laws to different processes in a power plant, then we could establish the expression of energy transfer, whether it is in the form of heat added to the system or it is in the form of work being extracted from the system. We could establish their expression. So, today you know that in particular we have seen that if we apply that form, mathematical form, to the process which is there in a boiler, also the process which is there in a turbine, and from there we could write the expression of, rather the mathematical expression of heat which is added to the boiler, essentially for the change of the thermodynamic state of the working substance, and for the turbine wherein we had seen that while steam is flowing through the turbine, it does work and we are getting work output. So, just for the recapitulation again, we can draw the schematic of the power plant. So, you know that only we can see the major equipment, boiler, turbine, condenser and pump. So, this B for boiler, T for turbine, C for condenser, P for pump. Okay. So, now though we have seen that the amount of heat which is needed to be supplied to the boiler for the conversion of steam and the amount of work that we are getting from the turbine, the mathematical expression of these two quantities we have established. One important, that also I had discussed that in a similar way we also can find out the expression of this quantity which is rejected from the condenser. We have also discussed that second law of thermodynamics puts a restriction that if we need to run this plant in a cyclic manner, there must be a provision of energy rejection. So, you know that this particular component, that is pump, if we try to apply that, if we need to know the this quantity, that is the amount of work that must be added to pump the condensate to the boiler, and what would be its mathematical expression. So, you know that this is we can consider that all the processes are ideal. So, this is constant pressure heat addition, this is reversible adiabatic expansion, and we have discussed that walls of the turbine are insulated, so that there is no heat leakage or heat loss through the wall of the turbine, and the process can be considered that it is reversible adiabatic process. This is also that constant pressure heat rejection process, and this is the last process which is important. Now, this is the pump, and if we try to recall, we will discuss today, also we shall be discussing this part in our subsequent classes, that the thermodynamic state of the working substance at 1 is liquid, in particular this is saturated liquid. So, when this pump is supplying the saturated liquid from this condenser to the boiler, and it is because of this pumping process we need energy input, that is W in the form of work. So, what is the process? Can we represent this process as a reversible adiabatic process, because you know that there is no heat interaction between the system and surroundings. So, if we consider the pump is a system and the surroundings, so there is no heat interaction. We also can consider the process that is there while condensate is pumped back to boiler, and this process can be represented by the reversible isothermal process. So, basically you know that boiler is a heat interacting device and the process is also a heat interacting process. Turbine is also a device in which there is no heat interaction between system and surroundings. Somehow in reality we really do not, we have to admit that in reality there must be some amount of heat leakage, but while we are trying to estimate the efficiency of the cycle, we also need to estimate the efficiency of the performance of all the processes which constitute together to form the cycle. So, in this particular device is a work interacting device, because we are getting work output. Similarly, this is also a heat interacting device, because this is required wherein heat must be rejected to operate the system in a cyclic manner. What about this? So, this device is not a heat interacting device, but we need to supply work for this pumping. So, if it is not a heat interacting device, so there is no heat interaction between system and surroundings, we can represent the process as the reversible adiabatic process. Can we represent the process by reversible isothermal process? Because you know that thermodynamic state of the working substance at point 1 is saturated liquid. So, while pumping, the state is getting changed and it is coming to state 2 where pressure is definitely higher, and that is what our objective is. But since it is an incompressible fluid, so there is no change in volume, specific volume is not getting changed, but can we really represent the process by a reversible isothermal process? So, you know that as liquid is being pumped from state 1 to state 2 or point 1 to point 2 by it is because of this, it is viscous liquid. So, it is because of this dissipative effect, temperature will be slight temperature rise will be there. So, maybe we cannot map the process by reversible isothermal process. Even if we try to represent the process by reversible isothermal process, what would be the mathematical form of this quantity which is required to be supplied to operate this pump. So, to do that we need to, so basically till now we have discussed about the mathematical expression of this Q in, W out, and in a similar way you also can calculate Q out. I am not going to discuss that. So, what about W in? To do that we need to understand little bit about second law, which is applied to the flow process. So, what we will be doing? We shall be doing the second law applied to flow process. So, you know that if any particular process concerns a flow across the system boundary. So, you know that the process, the pumping process, there is a continuous flow from 1 to 2. So, the process concerns a flow across the system boundary. Now, if we try to apply second law, why do we need to go for this analysis is very important. You know that essentially we are trying to apply second law to a flow process. That means we are trying to look at the entropy transport for a flow process. Why? See, you know that question is that when the process is taking place inside the pump, so entropy is getting changed maybe from state 1 to state 2. Now, what is the entropy transport with that flow, that we also need to know. Why do we need to know? Because we are trying to calculate this quantity W in, and while we are trying to calculate W in, alongside the first law of thermodynamics applied to flow process, we need to know the entropy transport for a flow process. So, I am sure that you have studied about change of entropy, the net change in entropy for a control mass system. So, knowing the net change of entropy for a control mass system, the expression of the net change of entropy for a control volume within a control volume can be mathematically written by how? If we know the net rate of change of entropy for a control mass system, we can mathematically write the expression of the net rate of change of entropy for a process across the control volume by appealing to the Reynolds transport theorem. So, what I would like to tell you that our concern is to express the net change of entropy for a flow process. We know how to calculate the net rate of change or net change of entropy for a control mass system. So, if we are targeting to write the expression of the change of entropy for a flow process, that is when the flow across the control volume, knowing the expression of that particular quantity for a control mass system, we can write it for a control volume by applying to the Reynolds transport theorem. So, we can write the Reynolds transport theorem, just the mathematical expression, although we have discussed it, but for the sake of completeness I am again writing today. So, this is dN dt for a system, that is dN dt control volume plus, that is control surface dA. So, if we try to keep it inside this box. So, this is the RTT. Now, our objective is to write the entropy transport, the change of entropy, rather we need to know the mathematical expression of the change of entropy for a process across the control volume, knowing the change of entropy for a control mass system, and to do that we need to apply this transformation equation. So, here this N is the total entropy. So, this is total entropy and small s, that is capital S by M, is the specific entropy. So, we can write that ds dt for the system equal to ds dt for the control volume plus control surface S rho dA. So, if I go back to the previous slide, this dN dt system, that is the net change of an extensive property, say n, within the system. Similarly, this is the net change of entropy within the system. This is the same within the control volume. So, this is within the control volume. What about this fellow? So, this is net transport of entropy owing to the flow across the boundary, Okay. So, basically you know this quantity left hand side we know, because the change of entropy for a control mass system we know. Knowing this quantity, we can write the net change of entropy within CV. To do that, we also need to know what is the net transport of entropy due to flow or owing to the flow across the boundary. Why? Because you know, as I told you that if we try to find out the mathematical expression of W in, which is needed to run the pump, we need to know this. Why? I will be explaining soon. So, what about this quantity? This ds dt for the system equal to q dot by T plus S dot generation, right. So, this is basically the change of entropy within the control mass system, that we know. So, this T is the temperature of the temperature of the boundary through which heat transfer takes place. So, heat is either being added to the system or it is being extracted from the system or taken away from the system. This T is the temperature of the boundary through which flow of heat takes place. So, this is temperature of the boundary through which heat flow takes place. Now, if we have multiple such boundaries through which heat is getting interacted between system and surroundings, we can write this is the expression. Okay. Now, it is very important. Now, what we can write is that, so we can write this q dot by T plus S dot gen equal to ds dt Cv plus, which is very important. If I can write this now S rho dA. We can take one assumption that, so if we consider that this is the control volume and we have this is inlet to the control volume and this is exit to the control volume, and control volume is changing from its state 1 to 2. So, this is in and this is exit. Okay. So, this is a flow system. So, this is flow in and this is flow out. Control volume is changing its state from state 1 to 2. Now, the change of entropy within the control volume, that is ds dt with Cv. Entropy transfer due to flow in and flow out, this quantity represents the change in entropy within the control volume due to the flow. Now, if we consider that this is the flow section. So, entropy specific is not changing in the respective flow section. Okay. In that case, what we can do, we can take out we can take S out from this and we can write, and this is the assumption. Before going to that, we can write, so q dot by T plus S dot gen equal to ds dt control volume plus S Cs rho V relative in cap dA. What about this quantity? This quantity, you know that this quantity is nothing but the mass flow rate. Okay. So, what we can write? We can write one step further. We can write q dot by T plus S dot gen equal to ds dt Cv. So, this convention we know that if it is outlet, outward normal and flow direction, these two are in the same direction, whereas the outward normal for the inflow is opposite to the flow direction. So, considering that we can write, so this is m dot exit into AC minus m dot inlet into SI. So, basically if the entropy which is coming in with the flow is SI and entropy which is going out from this control volume, that is SE. So, this is section E and this is section I. Okay. So, if we have in this particular control volume, so now we have single entry single exit, it is highly possible that within this control volume, I mean multiple inlets and multiple exits will be there. In that case we can write, we can modify this equation like this. Now, if we consider, because if you try to recall, we have discussed that one important assumption is that in this particular plant we are considering that all the processes are steady state steady flow process. So, if we consider the process is steady state steady flow, so for a steady state steady flow process, okay, this ds dt Cv equal to 0. So, this is for the steady state and steady flow. Why? If the state is steady, so this is for the steady state, for the steady state the no difference, basically if we look at this, for the steady state there is no difference between state 1 and state 2. So, the change in entropy and steady flow. So, we have discussed about the physical significance of these two coupled keywords, that is steady state steady flow. So, this is equation. So, ultimately we can write for a steady state steady flow case, we are getting this is q dot by T plus S dot gen equal to m dot E AC summation of m dot I SI. So, this is the equation, this is the equation which we shall apply along with the first law of thermodynamics to obtain the amount of work that should be added to the pump for the operation. Okay. So, you know that next we can discuss about two different processes. One is now case 1, that is steady state steady flow process but it is reversible isothermal. So, basically we would like to discuss about a process which is steady state steady flow, which is reversible and isothermal, right. So, if it is reversible and isothermal, this is the entropy transport equation for this steady state steady flow process. So, to arrive this equation we did this exercise. Now, though you are familiar with this equation because you have studied it in the thermodynamics course, but I have again derived it because it will be very much needed to obtain the expression which we are looking for in today's class. So, basically if we know that if it is single entry and single exit. So, now question is, if we look at this particular system and if we consider that any this is pump and if we consider control volume, at any instant of time there is only one inlet and one outlet. So, basically for single inlet and single exit for single entry and single exit. We can write, so this is q dot by t plus s dot jn equal to m dot AC minus SI. If it is single entry and single exit, we know that from the mass conservation equation m dot E equal to m dot I equal to m dot. Okay. Since it is reversible, because we are trying to have the expression of this W in for a process which is steady state steady flow process, on the top of that we are assuming that the process is reversible and isothermal. If it is reversible, then this is equal to 0. Right? Then we can write that q dot by t equal to m dot AC minus SI. So, we can write that this is in the rate form. So, we can write it in this form, that is q equal to t into AC minus SI, right. So, this is the equation which is written in the form of, in the rate equation. We can write q dot by m dot, that is nothing but small q, and that is equal to t into S E minus SI. So, this is very important. So, let me keep it inside this box. Okay. Now, we have to apply again the property relation. So, if we apply the property relation, that is TDS equal to DH minus VDP. Why? TDS is equal to du plus PdV. You try to understand, we are trying to establish the expression of W in for a process which is there in a pump. So, in this process pressure is changing. So, the sole objective of having this particular component in this circuit is to raise pressure from point 1 to point 2 or state 1 to state 2. So, if pressure is changing, then and that is also the, you know that this is this is a flow process. So, we need to write that is dH. So, thermal energy, that is not U. So, the thermal energy for the flow process is H, that is U plus PV. So, now this is dH minus VdP. So, you know that if we write it isothermal process, reversible and isothermal process, so T is not getting changed. So, basically we can write T into 1 to 2 ds equal to 1 to 2 dH minus 1 to 2 VdP. So, we can write that is T into S2 minus S1 equal to H2 minus H1 minus 1 to 2 VdP. Okay. What is T S2 minus S1? That is Q1 to 2 or Q. So, T S2 minus S1. So, this is the generic expression we could establish. So, we can write that this S2 minus S1 is nothing but Q. What about first law? So, first law for steady state steady flow process across the control volume. We can write, you know, Q dot plus m dot Hi Ci square by 2 plus Gzi equal to m dot I, m dot E, He plus C square by 2 plus Gzd plus W dot, right. So, we have seen that m dot I equal to m dot E equal to m dot, and we can write it in this form that cube plus h I plus c I square by 2 plus g z I equal to h E plus c square by 2 plus z E plus w. This is small w. Okay. You know that if we try to write that maybe this is the generic expression, if the control volume is changing its state from 1 to 2, we can write cube 1 to 2 equal to plus h1 plus c1 square by 2 plus gz1 equal to w1 to 2 plus h2 plus c2 square by 2 plus gz2. So, basically you know, if we try to write this quantity is q1 to 2 equal to h2 minus h1 minus 1 to 2 VdP. So, we can write this quantity 2 q12 from this expression. So, if we give this name of the equation, this is 1. So, we can write using equation 1 and say this is equation number 2, and finally, this is equation number 3. So, you know that q12 is equal to h2 minus h1 minus integral 1 to 2 VdP. If we write the expression of q12 in equation 3, so now using equation 2, we can write h2 minus h1 plus h1 plus c1 square by 2 plus gz1 equal to w1 to 2 plus h2 plus c2 square by 2 plus gz2 minus 1 to 2 VdP. So, this is the left hand side, this is the right hand side, right. So, q12 is equal to h2 minus h1 minus 1 to 2 VdP. So, what we can see, this h1 will get cancelled, h2 and h2 will get cancelled. So, we can write that w12 equal to minus 1 to 2 VdP plus c1 square minus c2 square by 2 plus g into z1 minus z2, right. So, this is very important form which we wanted to have. So, what you can see that the work done for the steady state steady flow process. So, the work done, that work which should be added. So, the energy which should be added in the form of work for a steady state steady flow process, which is also reversible and adiabatic, is nothing but minus 1 to 2 VdP plus C1 square minus C2 square by 2 plus G into Z1 minus Z2. If we consider the changes, if we do not consider the changes in kinetic and potential energies, then we can write that work done in a steady state steady flow reversible and isothermal process W1 to 2 equal to minus 1 to 2 VdP, provided when the changes in kinetic energy and potential energy are negligible. So, this is very important. If they are not negligible, we cannot write. If they are negligible, we can write this is the form. So, this is very important. Now, let us try another case, that is case 2, that is steady state steady flow process, but now the process is reversible and adiabatic. So, process is reversible as well as adiabatic, then what would be the expression of this quantity work done? So, you know that if we write from this particular equation that this quantity, so see that q equal to 0. So, we can write from equation 1 m into S2 minus S1 equal to 0. So, S2 equal to S1, that is isentropic process, right. Reversible adiabatic process is also called the isentropic process. Now, the property relation, which one will be used? TdS equal to dH minus VdP. Why? Because pressure is changing in this is a flow process in which pressure is changing. TdS is equal to du plus PdV, that is applicable to any processes, but in this particular process we are writing TdS is equal to dH minus VdP because pressure is changing from state 1 to state 2. So, basically if S2 minus S1, that implies that ds equal to 0. So, we can write dH equal to minus VdP. So, we can write it that H2 minus H1 equal to minus 1 to 2 VdP. Okay. So, this is what we can write. So, second law, if the process is steady state steady flow process and along with the steady state steady flow the process is reversible and adiabatic. For that process we know this is isentropic process. So, reversible adiabatic process is isentropic process because entropy is not getting changed. So, ds is equal to 0. Now, using this property relation TdS is equal to dH minus VdP, we could write that H2 minus H1, that is change in enthalpy is nothing but minus 1 to 2 integral VdP. So, this is property relation. So, this is obtained from the property relation, this is obtained from the second law applied to the flow process. So, now we write the first law. So, if we write the first law, reversible adiabatic process. So, basically you know that q dot plus m dot into h I c I square by 2 plus g z I equal to m dot into h E plus c I square by 2 plus g z D plus w dot. So, this is the equation in the rate, this is the rate equation. Now, this quantity is 0 because this is reversible adiabatic process. So, there is no heat interaction between system and surroundings. So, this is equal to 0. Okay. The reversible adiabatic process, that is ds equal to 0, isentropic process, adiabatic process, that is q dot equal to 0, single entry and single exit we could write m dot E equal to m dot I equal to m dot. Now, what we can write, I mean this is, so what is H2 minus H1? So, basically you can see that W1 to 2, so W1 to 2 is nothing but W dot by 1 to 2 by m dot equal to H1 plus C1 square by 2 plus GZ1 minus H2 minus Ct square by 2 minus Gz2, right. From the first law, what we are doing, we are writing W dot by m dot, that is nothing but W, small w specific work for a process, that is process 1 to 2, that is nothing but H1 plus C1 square by 2 plus Gz1 minus H2 minus C2 square by 2 minus Gz2, and that is what I have written over here. So, you know that we can write, so this is H1 minus H2 plus C1 square minus C2 square by 2 plus G into Z1 minus Z2. What about this fellow? H1 minus H2, that we can write, that is nothing but minus 1 to 2 VdP. So, this is what we got from the property relation. Okay. So, that is plus C1 square minus C2 square by 2 plus G into Z1 minus Z2. Okay. So, this is W1 to 2. Again you see, if we just ignore the changes in kinetic and potential energies, then the work done even for a steady state steady flow process, but the process is reversible and adiabatic, can be written W1 to 2 equal to minus 1 to 2 VdP. If we mark it, okay. So, if we write it, so this is for negligible values of the changes in kinetic energy and potential energy. So, for the negligible value of the changes in kinetic and potential energies, we can write, this is the expression. So, if we try to write that reversible isothermal steady state steady flow process, work done W1 to 2 equal to minus 1 to 2 VdP. For the reversible adiabatic steady state steady flow process, work done W1 to 2 equal to 1 to 2 VdP. So, we can see that the work done for the steady state steady flow process is generic. The expression of work done for the steady state steady flow process is generic, no matter whether the process is adiabatic or process is isothermal. So, the expression of work done for the reversible steady state steady flow process is generic, and it does not depend whether the process is adiabatic or isothermal. So, this is what is important. So, you know, our objective was to find out what would be the expression of W in which is added to the pump. If the process is reversible isothermal or reversible adiabatic, there will be a slight change in temperature of the flowing fluid because of the dissipative effect, and considering this, if we try to represent the process by using or by the reversible adiabatic process, even then the expression of work done is remaining same, that is nothing but minus 1 to 2 VdP. So, why it is so? So, basically you know that for a reversible steady state steady flow process, the expression of work done is same. It indicates that any reversible process, any a reversible steady state process can be reduced to a series of alternate reversible adiabatic and isothermal processes. So, just for example, so this outcome of today's exercise, that the expression is the same no matter whether the process is adiabatic or isothermal, the expression of work done for the reversible steady state steady flow process is -122 VdP. Why? So, basically the conclusion is that any such process, that is reversible steady state steady flow process, can be reduced to a series of alternate reversible adiabatic and reversible isothermal processes. So, basically if we try to represent the processes in Ts plane. So, this is S T. So, you know that say system is changing from state 1 to state 2. So, this is 2 and this is 1, right. Now, what I was discussing, that expression is same. So, basically the reversible steady state steady flow processes can be reduced to a series of reversible and adiabatic processes. So, let me erase it this point too. Okay. So, basically you know that, so this will give us 2. So, conclusion is any such process can be reduced to a series of alternate reversible adiabatic, that is vertical line, and reversible isothermal, that is horizontal line. So, that is what I am writing. So, any reversible steady state steady flow process can be reduced to a series of alternate adiabatic vertical line and isothermal horizontal line processes. Any reversible steady state steady flow processes can be reduced to a series of alternate reversible adiabatic and reversible isothermal processes. I did not write reversible again, but reversible adiabatic and reversible isothermal processes, reversible adiabatic, that is vertical line, reversible isothermal, that is horizontal line. Here I did not write the reversible word because the process is reversible. So, any reversible steady state steady flow processes can be reduced to the series of alternate reversible adiabatic process and reversible isothermal process. Okay. So, you know that if we try to summarize, we have discussed about the mathematical expression of the work done for both the steady state steady flow, reversible isothermal and adiabatic processes, and we have seen that the mathematical expression is the same no matter whether the process is isothermal or adiabatic. And from there we could conclude that any such process can be reduced to a series of alternate reversible adiabatic and reversible isothermal processes. So, this particular exercise will give us a clue about the mathematical form of the work which is needed to add to the pump for supplying the condensate from the condenser to the boiler. So, with this we complete our discussion on the basic of the first and second law applied to the processes which are there in the power plant. In the next class, we shall start our discussion from the ideal power cycle. So, with this I stop here today. Thank you.